Welcome to The Explainer. Today we're diving into a really fascinating research paper titled Where, What, Why, and Importance: Structured Defect Grounding for Text-to-Image Feedback. Basically, we're going to explore exactly how researchers are diagnosing and fixing those persistent, weird visual mistakes that AI just keeps making.
So why do photorealistic AI images still have these subtle, complex flaws? I mean, we've all been there, right? You generate this absolutely stunning, highly detailed image, but then you zoom in and, wait, that person has 7 fingers. Or there's just a bizarre, localized glitch that completely shatters the illusion. Validating why these models struggle with this stuff and how we can systematically teach them to stop is exactly what we're tackling today.
Okay, let's dive into this. Here is our roadmap for today. 1. The flaws in AI images. 2. The representation bottleneck. 3. Structured defect grounding. 4. Training with SDG-30K. And finally, 5. Diagnosis to alignment.
Let's kick things off with Section 1, the flaws in AI images.
It's no secret that text-to-image models generate incredibly photorealistic images nowadays, but they still exhibit these localized, subtle, and structurally complex failures. Despite how wildly advanced these models have become, they still trip up on very specific structural details. And the researchers behind this paper argue that to fix these highly localized failures, we absolutely require a completely new kind of instance-level feedback. Essentially, we can't just give the AI a generic bad score anymore. It needs precise feedback about exactly what went wrong.
Which brings us to Section 2, the representation bottleneck.
Now, what's really interesting about this slide is how it shows exactly how we try to point out errors to the machine right now. On one side, we have the current standard, which is heat map-centric representations. Think of this as a very vague symptom tracker. It's basically a blurry map that just says, hey, something is wrong over here. But on the other side is what researchers argue we actually need: binding semantic reasons to individual failures, meaning we need to tie a detailed, specific understanding to every single error.
There's a great quote from the paper that summarizes this huge bottleneck. The researchers state that the old heat map method is, quote, making it difficult to localize variable-cardinality defects and bind semantic reasons to individual failures. Now, variable-cardinality is just a fancy way of saying the AI might make a whole bunch of different, random mistakes in just one image. Traditional heat maps are honestly like a doctor just pointing at your arm and saying, you feel bad right here, without explaining the actual disease. If the AI doesn't understand the semantic reason for its failure, well, it can't learn to avoid it next time.
So let's move to Section 3, Structured Defect Grounding.
So the crucial point here is the solution they came up with: Structured Defect Grounding, or SDG. It's a method that casts text-to-image diagnosis as a structured set prediction by modeling each defect as a specific tuple. That sounds complex, but instead of that vague heat map we talked about, SDG forces the diagnosis into a very clear data package, a tuple. It predicts a specific set of facts about every single flaw.
Let's break down exactly what makes up this tuple, because it's pretty brilliant. It consists of 4 data points: location, where the defect is; type, what kind of defect we're looking at; reason, why it's defective; and importance, which ranks the severity of the flaw. This tuple perfectly acts as a highly detailed medical chart for AI defects. It tells the machine literally everything it needs to know to understand its own complex failures.
Next up is Section 4, Training with SDG-30K.
30,000. And this brilliantly illustrates the sheer scale of what they built. The researchers didn't just propose an e-concept, they actually built a massive 30,000 image dataset to back the whole thing up. Unlike your typical automated web scraping, gathering and structuring this specific kind of localized failure data across 4 different modern image generators is a massive manual undertaking. They really needed to ensure the AI learned from a vast, diverse range of possible failures.
So, the SDG-30K dataset features box-grounded annotations, accompanied by a dedicated evaluation protocol called SDG-Eval. When they say box-grounded, it means they literally drew precise bounding boxes around the exact locations of the flaws in the images, and then tied them directly to those detailed tuples we just talked about. This heavily annotated dataset provides the absolute ultimate training ground for the AI to systematically learn from its own mistakes.
Finally, we arrive at Section 5, Diagnosis to Alignment. Let's move along and see how this all builds into a complete, working pipeline. There are 3 crucial steps to this diagnosis to alignment framework. First, a vision language model, or VLM, serves as the SGD detector, kind of acting as the doctor that spots and categorizes the tuple. Second, a new mechanism called BoxFlow-GRPO converts those predicted defect sets into rewards. And third, Those rewards are used for diffusion model alignment. This is essentially teaching the model how to adjust its behavior to avoid making the defect in the first place.
Okay, step 2 has some heavy terminology, so let's carefully unpack it. BoxFlow-GRPO converts predicted defect sets into box-derived, importance-weighted spatial rewards. Simply put, this is the mechanism that translates the structured diagnosis into a tangible reward signal. It takes that bounding box, factors in the importance score from our tuple, and then gives the AI a spatial reward so it knows exactly where and how significantly it needs to fix the image. It literally turns a diagnosis into direct action.
So the big question, does it actually work? Well, the results are genuinely exciting. First, the SDG detector outperforms leading proprietary VLMs on structured grounding. It is remarkably capable of finding and organizing these complex flaws. Furthermore, utilizing these rewards consistently improves text-to-image alignment and actively supports localized image refinement. By using this structured tuple feedback, they prove that yes, you absolutely can successfully guide the AI to fix its own structural blind spots.
The researchers sum up the ultimate impact of this perfectly in their abstract, stating, quote, "These results establish SDG as a unified, instance-level interface for diagnosing, evaluating, and enhancing modern generative models." So they haven't just created a simple patch here. They've essentially established an entirely new language for AI self-correction, moving the whole field far beyond the era of those vague heat maps.
Which leaves us with a pretty provocative final thought. How will structured defect grounding change the next generation of AI art tools? Because if models can accurately diagnose the where, what, why, and importance of their own subtle flaws, we might actually see a future where AI self-corrects structurally complex errors before we even see the image. It's a real game changer. Thank you so much for joining me for this explainer, and keep exploring.